first step in having an excellent extrusion comes from having a consistent nozzle temperature. If your temperature on the nozzle is swinging around by 3 degrees in either direction from your target temperature, that can lead to some minor under-extrusion and over-extrusion, which can come into play when you're printing flexible pieces, that like the little flexi dinosaurs or just the little gadgets that you find on Thingiverse. So the way that we accomplish having a consistent nozzle temperature is through a PID tune. The PID tune will repeatedly heat and cool the nozzle and do some calculations in order to give us some numbers that we will plug into the printer's firmware to give us that consistent nozzle temperature. As we are going through the PID auto tune, the nozzle does heat up to the target temperature. For me, that's just around 200 degrees, and as you can see, when my nozzle is hot, I get a little bit of nozzle ooze coming out. So to keep our nozzle nice and clean, I'm going to lower the bed. And it's pretty easy to do, at least with the Ender 5 Plus. You just type in the amount of space you want between the nozzle and the bed. Oh well, 500 is a bit much. We'll just go for a solid 150 millimeters. And here we go. Once that finishes lowering, we're going to transfer over to the computer and start the PID auto tune. Now that we've transitioned to the computer, we need a good way to be able to send and receive values and lines of G-code from the printer. A lot of people think that you can accomplish this with any version of Cura, but as they all eventually figure out, you can only send lines. Nothing really ever comes back, or at least I've never had success with it. This is where I come in with Octoprint. Having this Raspberry Pi allow me to wirelessly control my printer has been one of the best $30 I have ever spent for all of my 3D printers. It's very convenient and can give you some nice charts, which really helps in making these videos for you guys. So the first thing that we do in order to start this PID tune, now that we've saved our M503 values in a safe place, is to type out M303 E0 S200 C5. M303 tells the printer to run a PID auto tune. E0 says run it on your first extruder. If it's your only one, just keep the E0. The S200 specifies your target temperature. I like to run most of my filaments just around 200 or 190 degrees, but I'll run my target at 200. The C5 is how many times it goes through a fluctuation. The more times you do it, the more accurate your PID values will be, and the more consistent your nozzle temperature will be throughout the entire print. So in order to start this off, I have my M303 values typed in. I'm just going to hit send. We can see right here, the printer has received the PID auto tune start. It's setting temperatures, and we can come over here. We can just barely see the beginning of the PID auto tune as it heats up to its initial temperature of 200 degrees. I'm going to leave this running. I'm going to walk away and eat some snacks while this runs. And we're back. We can easily see that the printer has gone through a PID auto tune a cycle of 1, 2, 3, 4, 5 times. Now what we need to do is to come through all of these little status messages and look for our new PID values. Just above it we can find our PID auto-tune finished. If you can't find it right off the bat, go ahead and hit this copy all and paste it into a text file so that way you can use a good search function. Now that we've found our new PID values, we need to submit that to the printer and have it save. The easiest way, just get your M301 or grab your original M301 values, paste it in, and then just change what we're plugging in. Plug in the same value for where it comes from. I will come here. Some of you will find that these values change quite a lot, but they should. If your temperature is swinging wildly, they should change drastically, and then if you're pretty close, they should stay fairly similar. But now that we have this all ready to go, just hit send. The printer has received it with OK, and in order to make this remember these values, if we turn off the printer, save it to the EEPROM by typing M500. And we can see right here, settings stored, and we are good to go with a very solid temperature tune. Now that we've wrapped up and saved our new PID values, it's time to make sure that our extruder motor is properly calibrated. On the Ender 5 Plus, the extruder motor is not the y-axis right over here, but this. The first step in calibrating your extruder is to have a way to measure a distance that the filament will move as the extruder turns. I like to use my Phillips brand calipers. Actually, Phillips makes shavers. Pittsburgh makes calipers. I picked these up from a local Harbor Freight, and they've served me quite well. What you want to do when you are calibrating your extruder and finding out the initial length is to be able to have a common place to put your caliper. As you can see, mine runs right off of the filament out sensor. I ballparked 120 millimeters and placed a mark with a mechanical pencil on the filament. This ended up being at just over 130 millimeters. Now we need to tell the extruder to spin 100 millimeters of filament through. Once it turns that amount, we'll go back to the printer and measure the remaining distance. And here we can see that the extruder is making quite a mess. I'm happy that I lowered the bed, and you can see the gear slowly turning back here. Once it finishes moving the 100 millimeters, I am going to measure the length of the mark from the filament out sensor, and then we're going to figure out the correct E-steps per millimeter. So I've come back from measuring 3 more times, and it turns out that this first initial distance of 95 millimeters was pretty bad. So I kept measuring and found out that my more consistent results was 85.46, 85.53, and 85.76. So those are the 3 values that I'll be using. And now we can see that my extruder was pretty far off. It was 15 millimeters short, or it was only extruding 85% of what the G-code was telling the printer to do. So now we need to figure out our new value. So what we need to do is come over here, grab our M503, and we're going to look for the M92 line. That's near the top. It's our steps per unit. So we see M92, we come over here to E, which is our extruder. Right now it's set to 93 millimeters. What I'm going to do is I'm going to calculate the average of the values that I measured, and that average is 85.58 millimeters was extruded on average. Oh, hello calculator. So, using that value, we are going to take our old steps per millimeter of 93. We are going to multiply that by 100 millimeters because that's what we told it to do. Then we are going to divide by our measured length, which is 85.58333 repeating. And that gives me a new E-steps per millimeter of 108.67. Most of these positions that we plug in only go to 2 or 1 decimal places, so be as accurate as you want. To type in the new line, I just hit M92, E, and now I can't remember what the value was. We do 108.67. Press enter, and we can see that the printer has accepted this new value. We hit M500 to save it to the EEPROM, and just to make sure it changed, we can type M503 again and find our new value of steps per unit, M92 E108.67. The third section in getting to perfect extrusion is making sure that your line width is actually coming out to what it needs to be. Right now it's set to 0.4 millimeters, but I really don't know what it's coming out as. It could be at 0.38, 0.45. If those values are off and you try printing a little tolerance test, you'll be lucky to get your 0.5 millimeter gap to be able to move inside of those tolerance tests. Or if you have a movable print, it won't move because it's fused together because your printer is pushing out more filament than it needs to be. As we can see, I've heated up the bed in my printer, so that way when we slice this 20 millimeter cube, it can be ready to go. Alright, so we come over here, and in order to get a good measurement on your line width, is we're going to use something that's frequently referred to as vase mode, but in Cura, it's hidden under special modes and it's called spiralize outer contour. What this does is it makes your model only have one wall all the way around, and the z-axis moves smoothly up the print instead of laying down a single layer at a time. It won't show this in the print preview, but the z-axis does move smoothly all the way up the print. As always, take a quick look at the print, see if you're happy with it. With the skirt, the number of bottom layers won't really affect this, but as we can see, it's a single wall going all the way up. The issue that using this smooth edged 20 millimeter cube is we can see up here at the top, it's a smooth edge, which means if we take our calipers right when this finishes, this line width value will be a lot larger than what it actually is. So once this finishes, I'm going to take an X-Acto knife and cut off the last couple top layers. And then I'm going to measure in 8 different places, about 2 or 3 on each side of the cube, and average that value out. Alright, so I have just averaged out all the values that I have measured. I recommend taking those measurements right around the middle of each of the sides of the cube, because that is where your speed is the most consistent. As you measure closer to the edges, you may find that the wall thickness becomes larger because your printer is decelerating and running slower near the corners. But I found that my walls were coming out at 0.53 millimeters thick, which is really thick when it's only supposed to be 0.4 millimeters. So in order to find out my new flow percentage, I just take my old line width, which is what should be coming out of the printer, which was 0.4 millimeters. I like to keep it to that value to the same size as the nozzle opening. And then the old flow percentage was just the standard setting in Cura, which is 100%. So I multiply by 100. And now I will divide it by the average line width from my cube, which was 0.53. So divide by 0.53 gives me a percentage of 75.5%. Most people end up finding that their printer works well with a 90% flow. It just depends on the printer. Apparently mine likes 75%. I have a Anycubic Chiron that I affectionately call Karen, and the flow percentage on that machine is at 85%. That is fitted with a direct drive full metal E3D V6 hot end that I was gifted. So it just depends on the extruder, and it also depends on the filament type. I recommend checking each type of filament, whether it's PLA, ABS, TPU, ASA, PETG. You really should do this entire process for every single type of filament. But we'll save that for another video. Now we just need to somehow submit this 75.5% into Cura. And what we're going to do is just change the flow setting. So we come into material and change the flow, and I'll leave that at, we'll call it 76%. This is a personal preference for me. I like to leave my initial layer flow higher than the flow throughout the rest of the print, just because I find that allows for excellent adhesion of the print throughout the entire build time. Very rarely will I have a print fail because of this. So I'm going to leave this, and let's just say, I don't know, 94%. I'm just pulling that number right out of thin air. But this should still allow for excellent adhesion. If I start to have issues, I'll take it back to 100%, and I should have perfect layer adhesion. That wraps up this video. I hope you've learned a lot.